Hello, everyone. Let's discuss another Leetcode problem. Today's problem is problem 211, design, add, and search words data structure. And this is one of the problems in the blind 75 list. So let's look at the problem discussion. We have to design a data structure that supports adding new words and finding if string matches any previously added string. Okay, so sounds like something like try, probably, right? So we have to implement, we call this data structure word dictionary. Word dictionary, this constructor initializes the object, and then add word, where you give, like, send a word as send the word string as parameter. We'll add that word to the data structure, which can be matched later. Later on, you can use this method, search word, where the word is given parameter, returns true if any string in the data structure that matches the word or otherwise. Now, here is one important thing. The word, that means the parameter that you are sending inside the search method, that thing may contain dots, where dots can be matched with any letter. Okay, that totally makes sense. Okay, so my data structure's name is word dictionary, obviously, and from the description, obviously, you understand that the try might be a good, like a substitute, or actually, it's the word dictionary is a try, right? And then you can add words, say bad, dad. We are adding 3 words: bad, dad, mad, right? And then we are searching for pad, which will return false, obviously, because it has not been added yet. And then we search for bad, which turns out to be true, right? Obviously. And then we search for dot ad. Now, here is the interesting thing that's happening. You see that dot can be matched with any character. So if I am searching this dot ad, what it's doing is going to the data structure and then going to the root and say it's matching any character. Say it matches B, it's fine, right? And then after matching B, is looking for the rest. So what is the rest? The rest is AD. So if you have bad and you are looking for dot AD, the dot matches any character, and then you match the other portion and return true, right? And the constraint says that there might be even more than one dot, so it might be something like that, dot d. So what's going to happen here is, you see, suppose this one will match B, this will match A. We say like it will match any character, and this one is going to match D. Okay. The other constraint says these are so for the constraints, you have to ask the interviewer, like, what is the type of the characters that can be inserted into the data structure. So it says the word length is less than 25, and that means the data structure can have at most 25 levels. And this is the important one. The words can contain only lowercase English letters. Okay, so okay. And okay, so lowercase English letters, and it can contain dot. Okay, word in search. So when you are adding words, obviously you're not adding dot. We're just adding real words with lowercase English letters. But when you're searching, your word can have dot and any lowercase English letter. Okay, so as we said, like, if you're familiar with try, this one very much looks like a try, right? If you haven't watched my lecture on try, I would strongly recommend to watch that. It will give you a very nice foundation on, and you will build a nice concept on try. and you can use that concept beyond this problem. Okay, so if you're not familiar, we can still talk about it here, and you can just follow the lecture here, and you can understand. So what's going to happen is we are going to build. So for this word dictionary, we are going to build a tree kind of a structure, which will have a root. Initially, it will have a root, and then it will. So when you are actually adding bad, we'll actually create a node. So we call this a try node. For B, we create one node, try node. Then for A, we create another node. And then for D, we create another node, right? For SAD, this is the root, okay? And then for SAD, we create a node for S, and then A, D, right? Okay. So inside every node, we are going to have this list of children. So the list of children is going to look like this. As I said, like in the constraint, it said that it can only have like lowercase English letters. So the first index, and so we can have just a list of 26 because there are like 26 English characters, right? So this one is actually, I'm showing it here. So this one will represent A, this one will represent Z from index 0 to 25. Okay, and initially everything is going to be, say, null, right? Everything is going to, when I first initiate this, everything is going to be null. But next time when I insert children, say A, what's going to happen is I'm going to create this, and then point it from here, okay? So this is more or less how try looks like. And also, these nodes will have another thing inside it. So a list of children and a Boolean. So there's a Boolean is word, just to mark the ending of a word. So you see, when we inserted BAD, it was like something at the children like this, right? So this was a link for the A, still it was null, but for the link of B, basically it was linking from here, right? And when you reach D, it's the end of the word. So for these node, is word equals to true. But for these node, these were false. This is also, is word was also false here. Okay. So more or less, we gave you the idea about the try. Now, let's look at one example. Say we want to insert, this, and then search for, say, let's search for dad and dot ad. Okay, so when you want to insert, obviously our word dictionary data structure will have a root node, and any try node is going to have a list of children, an array of, say, size 26. Initially, all of them are going to be empty or null. So when you're inserting sad, first it will go to the root node and look for the index of S. So we know how to get that index, right? From character, if we subtract the ASCII value of character A, we'll get the index. Index is this. We'll go and check if that index is null or not. If that's not null, that means already there is a node for S. But in this case, you see there is no node for S. So what's going to happen is we are going to create a node for S, right? And then link it here. Okay. And next, we're looking for A, right? And as you see that this one also has a list of children, and we'll go and check the first index, nothing there. So we will create a node for A and link it here, right? Next, similarly, D is not a child of A, so we're going to create a node for D. Okay. Similarly, we'll create nodes for G, because G is not there in the root yet. Then O, and D. Let's insert another word, say. Okay, this time we first will go to the node and look for S. Now you see that already we have a node for S, so we won't create another one. Inside S, you will look for A. Now you see we already have a node for A, right? So already have it, so we won't create another. Now inside A, we look for Y, right? And as you see, the only child that A has is D. So there is no child for Y yet. So Y is going to be here, right? Okay, so what we are going to do is we are creating a node for A and make this isWord true. Also, isWord is true here. Okay. Okay, that's it. Now let's look for searching. We're looking for dad. So when I go here, right, I will go to the root first and then look for the child for D. And as you see, there is, so suppose D is, I'm just, so say D is A, B, C, D. And as you see, this is still null. So there is no child for D. If there is no child, then obviously I will return false, right? Okay, and now let's look for, say, another word, G, gray, something like that, okay? So we will go to the root and look for the character G. And as you see, already there is a node for G. So we are fine with G. Next, we look for R. And as you see, there is no child R here. There is no child R. So we will return false. Okay. Now the interesting one, which is .ad. So here is the thing. If you have .ad, what are you going to do? So as you know, the description says that dot can match any character. So we're going to root and going to ask the root, hey, do you have any character? I'm fine with any character. So we can run a for loop and start checking if any character, if there is entry for any character. So what's going to happen if I run a for loop here? There is no entry for A, B, C, D, anything, but there is entry for G, right? Okay, fine. It says, okay, fine. If you have a entry for G, then okay, I will go there. And what's my challenge here? From G, I just want to match AD, right? So dot found a character G. It went there and then it's looking for AD. But as you see, there is no pathway for AD beyond this, right? So we'll return false. So we are not done there. With G, it failed. We will just keep on checking. Oh, do you have any other children? Do you have any other children? Yes, it says I have another children, like in the for loop S, right? Okay, fine. Dot now comes in this direction. Next, its challenge is to find AD. And as you see, there is a pathway for AD. And when you reach there, it says end of the word is true, right? Okay, then you are absolutely fine and you are finding it, okay? Now, here is one interesting thing. So dot A, if someone searches for dot A, so obviously you see that when the dot text finds a children in S, comes in this direction, its next challenge is finding A, right? It finds A, that's fine. But the thing is, each word is false here. So still it will return false, because that's not the end of the word. Okay, so the simplest trick here is when you find a dot, say, look for S dot D. So you come to S and then dot, it runs a for loop for everything and it finds one children A. So with dot, you come here and then you look for D and you come here and you see that is word is true. So you return true. Okay, so the simplest trick for dot is when you have a dot and then the rest, what you do is you are in a node, right? So for the dot, just look for everything. Just look for everything and say there is one here, one child here, and one child here, right? So with dot, just go here, and this is the rest of the tree, right? So there you ask, hey, do you have, say, this portion? Do you have this portion? You may find it or not. If you don't find it, if you find it, then yes, we return true. Otherwise, go to the rest of the tree. So take the other path for the dot, because dot can match any character. So take the other path and then come to this tree and ask this tree, hey, do you have this part? Yes or no? Okay, so let's code this and then it will be more clear to us. As told in the explanation, we need a class for try node. Let's name it try node. And then inside the try node, we are going to have, say, we can keep a value, a list of children, and then we are going to have a Boolean is word. The constructors for the try node, given a character C, and have it where the value of the node is going to be assigned, the value, the character is going to be assigned as the value of the node. We'll create a list of children. For these problem, there's a constraint that the children can be like only small case letters are going to be part of the word. So 26 children is fine. Each index will represent a character from A to Z, and each word, let's say, just we initialize it with false. For the root, obviously root doesn't have any value, so we can have just another kind of constructor which doesn't take any value. Still we are fine, because a node can have no value or something like that. Okay, so our Wiktionary is actually a try data structure, and it will have a root node, right? When we are initializing the Wiktionary, what we're going to do is we are creating an instance for that root. We will create a try node. Okay, so our initialization of the word dictionary data structure is done. Now adding words, the word has characters in it. So what we're going to do is, obviously we have to start from the root. So we'll have a try node. We'll reference it to the root, and then we'll read characters from this string. Okay, so for each character, we'll check if there is already try node for that character, right? So we'll check if node has a children for that particular character at that index, right? Sorry, yes, it has a children for that particular character. If that is null, that means there is no children yet. What we do is simply we create a node for that character and assign it as a children. Let's put the character, okay? Otherwise, like, yeah, but so by now we have a children. Either we created it or there was it from before. So what we do is we just assign the children as the next new node, right? Because next we are going to go one step down to the children and look for the rest of the word, right? Okay. Okay, we'll go to the children and then we'll look at the next character. And finally, once we are done, we are at a node, which is the last node for the try node for the last character. So we're going to set the is word thing as true. Now for the search part, we know that if we find a dot, right, it will be able to match any string, and then it will ask for the rest of the string to be matched to the subtree. In the explanation, you saw that if we have a dot, it can match any character, but for the rest of the string, it has to be matched in the subtree, right? In the subtree. So that means if we find a dot, in that case, there are two things that needs to be done. First, we have to go to the like match any of the children and then ask for the rest of the substring to be matched to the in the subtree, right? So we need to track two things. One is the substring and the other thing is the subtree. So for that, let's make another method, a helper method, say call it search helper, where we'll pass a string. So this will have the substring now, and then we'll also pass a node. This will have the subtree. Okay. Okay. So what we are going to do is we are going to read from the string. So if that character is a dot, then we are going to check every children inside that node, inside that try node. We know that for this problem, we can have at most like 26 children. We'll check if there is a children for at that specific for a specific character, then we will look for the rest of the string. So the rest of the string is defined as substring. Yeah, so it will be like I plus 1, right? Because we are at I index. And as for the subtree, we are going to pass the rest of the tree, right? So this is the start of this new tree. So if the dot matches with any character, what we're going to do is we are going to recursively call search helper for the rest of the string, right? Starting from I plus 1 index, and look for it inside the subtree, right? And if that is true, then we return true. Otherwise, we are going to look for the next children and the same thing. Okay, so if none of these succeeds, that means if there is no return happening, that means we didn't find anything, we return false. Okay, so that's how we handle a dot. Else if the node, so else if we have a real character and we see that there is no children for that character, then obviously you're going to return false, right? But the third case is if we found a character, we have found a real character, and then we also found a child for that character. Next, we are going to do is we are just going to go down to that child and do the rest of the work. And finally, we have, if we are here, that means we have reached, we have found all the characters, right? That's why we are here. Then we return node is word equals to true, okay? So it's not, so that means all the characters have been matched, but still we have to match if that character, the final character, is a ending of a word. Okay, so we had this search helper. So next what we can do is we can just call this search helper with the word as parameter and root, because this is the root of the try or the root of the word dictionary. Let's run this. Accept it and submit. Okay, so this got accepted, and we'll come back with another problem, and thanks everyone for watching.